Hi, I'm Dillon Krasovec. Today I'm going to demonstrate an augmented reality technique that'll fix images to a real scene in real time. As you may already know, typical augmented games utilize a gyroscope to capture relative movement, and then they use that relative movement data to offset the images on the screen accordingly, making it seem as if those images on the screen really exist. However, what developers learn quickly is that the gyro has this annoying habit of drifting, which could cause your augmented features to float away off the screen. The common approach I see online is to complement the gyroscope with an accelerometer. However, I want to try something a little bit different. For this approach, we will instead complement the gyro with image processing. To help demonstrate this, you can see I just set up some basic graphics for a first-person shooter game. The technique would be to extract a feature from a real scene at the beginning of the level and use that feature as our absolute position for calculating the gyro drift, and then to subtract that drift error from our augmented features for a smoother AR experience. For speed, I integrated a GPU library that allowed for faster processing of each frame. For initial processing of the raw image, I opted for a hair's corner detection, which I noticed had pretty good accuracy for its speed. All of these red crosshairs are corners that have been detected from that. For the second level of processing, we'll want to extract a feature. For this, I originally implemented an S-link clustering algorithm. However, I noticed that the cluster tracking wasn't quite accurate enough. So instead I came up with the following. First, we pick our feature by counting each of the corners across a few frames and picking the most reliable ones. You can see our feature that was selected show up in the green crosshairs here. Once we have our feature, the harder part is then to try and match it every frame. For this, I use my own technique. It's pretty rudimentary in concept, in that I just check to see if the distances between the corners match those of the feature, but it gets complicated when trying to find it within a bunch of other corners. I just use a depth-first search algorithm to cycle through all the corners and attempt to match. You can see that each time a match is made, the green crosshairs of the feature are visible. And when moving around the screen, you can see that the matching is pretty good and reliable enough to help us calculate the gyro error. At this point, I learned that the drift of the gyro was not as constant as I expected, and in fact varied quite a bit. So to manage this, I implemented a PID control system that would manage the dynamic error with the help of our feature, which we already have. I will demonstrate this by firing a bullet, and we will allow the gyro output to drift for a few seconds before syncing back up with our feature. And on each sync, we see that the distance of the new error is fed into our PID controller, and this will continue for the runtime of the application. And after a few iterations, we find that our dynamic gyro error is pretty good and stable. And now we could see the gyro, feature matching, and PID controller all working together pretty nicely. Anyways, it's still a work in progress, but that's the gist of the approach. Thanks for listening.